Welcome to Stir Trek. So, there's the mic. Before we start, I just want to say I think you all are completely awesome people, and I want to tell you why. You guys all, gals, everybody, came into Stir Trek, 9 a.m. first session. You looked at the schedule, and you said, I'm going to the math lecture. So,
yeah, baby.
You are my tribe. So, thank you for coming. That may not be the most exciting introduction ever, so let me try something else. I want, in keeping with the theme of this event, can we get the mic just maybe a little bit lower? Thanks. I want to give you a superpower. I want to give you the ability to look at a problem, a hard problem, and see a solution that you couldn't see before. I want you to leave here with the set of problems you can solve with a computer just a little bit bigger. So let's see if we can do that. Okay. This is really the only notes, hopefully, that you need to take here. My slides are already online. You can pull them down off a speaker deck. The presentation's pretty heavily hyperlinked, so if I talk about an interesting paper or a magazine article or something, and you want to look into that later on, the links are in the PDF. So you can pull that down off a speaker deck, or you can just watch it live on the site there. I'm going to run the full hour. I'm not going to have a separate question time at the end of the presentation, but I am very happy to take your questions, so please just feel free to raise your hand and shout out. Or, don't raise your hand, I don't care. It'll work fine. Having a little issue with my remote here. So machine learning is full of jargon, and there's some math here and there. But if you can get over the jargon hump, the concepts aren't really so hard. Basically, if you've done test-driven development, it's not going to look entirely unfamiliar. We're going to write some tests. We're going to run some solutions by the tests, and we're going to see how they do. And it takes remarkably little code, actually, because instead of writing code to make the test pass, for the most part, we can experiment with some different off-the-shelf modules, and we can try some different parameters, and we can just experiment and see what gives us the best solution. It's even easier on Azure because you have nothing to install. The amount of unusual programming languages, I'm presuming many of you do Java or C# or things like that, and in the machine learning world, we often use R and MATLAB and Mathematica and some other things. So using Azure Machine Learning makes that learning curve a little bit lower, but really important, there is a lot of jargon in the machine learning space, so I just want, if you hear me use a word and it's not clear what it means, I'd like you to call me out, just say, what's that? Can we practice here, everybody? Say, what's that?
What's that?
So if I hear you say that, I'm going to step back and try and kind of explain the words I'm using in the presentation. Okay, so a little bit about the history of this presentation. I originally did this as a 2-hour live demo at the Cloud Computing User Group in town, and I have compressed that down to 1 hour, so obviously I had to leave a few things out. But that makes the presentation a little bit user configurable. I can, put it more towards this end here with the machine learning basics, or I can talk exclusively about the Azure features, or I can do something somewhere in between. Azure tries to reduce the amount of sort of machine learning background and scholarly work you will have needed to read in order to produce working machine learning systems. However, it doesn't completely succeed. It does assume some familiarity with the space. Can I get a sense here? Who here has completed the Coursera machine learning course? Okay, just a couple of people here. So I'm thinking it might make sense to put the slider more towards this end of the scale. Does that make sense? Okay, we're going to go along with that. So I'm going to just a few examples here of problems that are commonly solved with machine learning. Obviously, I'll be talking about this first one, diagnosing cancer, a bit more than some of the others, but you will have encountered many systems in your everyday life that do use machine learning. Spam filters are a pretty big success. They've made email usable. The recommendations you see on Netflix or on Amazon Even the algorithms that determine the pricing on Amazon use machine learning. If you ever go to Paris and use your credit card, you probably got a call from your credit card company because they noticed that charge was maybe a little unusual. It's been very successful at doing voice recognition and language translation. I'll talk a little bit about that later. And this is sort of interesting that this paper here that I've quoted that managed to identify cat videos on YouTube. The really fascinating thing about that is that in machine learning, we talk about supervised algorithms and unsupervised algorithms. And in a supervised algorithm, you give it examples of things, and you say, this is a cat, and please find me other cats. But this work here was actually done with an unsupervised algorithm. The machine learning system was able to figure out what a cat video was just by looking at YouTube, without any human being, giving the algorithm the idea of a cat. But these are kind of complicated systems, and we're just getting started, so I'm going to talk about something a little bit simpler. I wrote a function down here, and this is C# syntax, but hopefully it's pretty clear what this thing does. If I were to give you this function, it's pretty easy. I suspect many of you are programmers. You could probably produce that curve. That's not a terribly difficult programming problem. But a question, what if I gave you this curve here, and I ask you to give me the function in return? That's a little harder problem, right? And maybe you remember some of your high school algebra, and you're able to recognize that function there. And you say, well, that looks like a parabola, and I can probably wing that through. It's got some parameters. There's, the location of the focus here, and there's some coefficients on there. You might be able to recognize that. So in this case, the data that I've given you is this curve, and the model is the idea of a parameter. And when we talk about machine learning algorithms, we're basically talking about we're going to figure out what the right model is for the data that we're given, and then we're going to have one other thing, which is a cost function. And the cost function is just going to compare the data with the results of our model and tell us how close we got. And essentially the problem we're trying to solve in machine learning is to make that cost as low as possible. In mathematics, we have a notion of optimization, which is different than the notion of optimization we have in programming. In mathematics, the notion of optimization is just to make the result of that function as low as possible, maybe close to zero. It's not always good to have it exactly zero. We'll look at why. But we just want to say we're going to tune the parameters to our model, and we're going to try and make the cost as low as possible. So I wrote a function to do spam classification. How's this look? You think this is going to solve my email spam problem? It's not a very good function. So one of the problems is that it doesn't work. And I could spend a little more time on this, right? I could make my function bigger, and I could make it bigger, and I could make it bigger, and maybe I want to include other trigger words, and I might want to include other headers, and it still isn't going to work. And the reason why we know it's not going to work is that people tried this. There was a system called Spam Assassin a long time ago that essentially took this to the nth degree, as far as you could go, and it still didn't do a very good job at classifying spam. Even if I were to expand this to the point where somehow, for my email only, it did do a good job of classifying spam, I'm probably not going to be able to maintain that code, right? It's going to be enormous, and good luck trying to keep track of the interactions of the different rules in here. And the other thing that makes this not really an effective spam detection algorithm is that some people actually like LinkedIn emails, I guess. I mean, they send them. I suppose there are people who like them. So my notion of spam is not going to be the same as your notion of spam, and everybody needs sort of a personal system. So we need something a little better. Here's another problem. This is a pretty common, this is kind of a hello world of machine learning here. I want to write a system that takes these images here, and these images are 20 by 20 pixels each. So essentially this is a function with 400 inputs. and 400 arguments. And we could roll that into a single image argument, and then, like, you know, maybe it would pass FXCOP, but I haven't actually made the problem any simpler. We still have to consider the values of those 400 pixels when we're trying to recognize the characters. So I don't think anybody could write code like this by hand. You might be tempted to try something, well, like I'm going to recognize the outline of this character, and then I'm going to look for things that look like a 5, but that might not actually be the most effective algorithm for recognizing the handwriting. If you're actually just going to consider the values of the pixels on one image versus the other, it's probably not something that you can maintain and have it work. So we need a different approach to that. So here's something, I'm a reasonably okay programmer, but I actually don't know that much about oncology or biomedical imaging or any of these things, but I'd still like to contribute to the greater good of womankind, by creating systems that do good things for the world. So I'd like to see if I can help out by making a system that can look at an image of a tumor and try and identify if it's benign or malignant. But even if I'm working, so because I don't have that domain knowledge, I might work with a domain expert, right? But the domain expert is going to speak the language of oncology, and I'm going to speak the language of programming, and there's always a little bit of an impedance mismatch there, where maybe we're not communicating as efficiently as possible. So I'd like to have a way where even if we don't totally speak each other's language, we can work together and come up with a system that at least gives good results. So I'm going to back up a little bit and kind of move away from practical real-world applications and start to look at some basic examples of how this stuff works. So in the first example I gave you, that nice tidy parabola, all of the points in the example data fell on a curve, and it was pretty obvious what the function was. Again, if you remember back to some algebra. In this case, we have some example data here. These blue dots, they don't clearly fall on any model. Maybe the model is a probability density, or maybe the model is just a straight line. It's not 100% clear just from looking at the picture. So in the world of statistics and machine learning, we might say that this is a system with error. But it's not clear where the error is, right? I mean, it could be that I have some measurement error in those blue dots. It could be that in the real-world system, it's perfectly reflected in that red line there, okay? Or it could be that the real world doesn't actually fit a really tidy model. This is your y equals mx plus b line on a graph here. And so it's not clear just in looking at the picture, is the error in this diagram, does it come from the measurement, or does it come from the imperfection of the model? This is why you can't just throw data blindly at a machine learning system and necessarily get a worthwhile result. You have to have some knowledge of the domain here to say, where do I expect the error to be, and how can I make that as small as possible? Like if the error was in the measurement of the blue dots, maybe I need to go back and collect better data. Maybe it doesn't even make sense to try and solve this problem until I get some more accurate measurements. If the error is just, the model is too simple for the real world, then I could live with that, or I could try a different model. So again, in this example, we have some parameters on our model, okay? We have the y-offset on the graph here, and we have the slope. And this is a pretty linear regression to a pretty simple model, so we have pretty simple parameters. A lot of other machine learning algorithms are considerably more complicated. So some of that sounds a bit like statistics. Anyone taken a statistics course here? Okay, lots of people. Awesome, you are my tribe. Okay, so there is some considerable overlap between machine learning and statistics, but they are not the same thing. So I'm going to just sort of overgeneralize a bit here, and I'm going to say Statistics is intended to be the gatekeeper of the sciences, right? You know, when you take your physics course and you're throwing bowling balls out the window and you're seeing, you know, for each bowling ball, how big's the crater in the sidewalk, you know, you plot those and you know the 20-pound bowling ball makes a huge crater and the 8-pound bowling ball not so big. But, you know, you don't really have something that's a publishable journal article until you can show statistical significance. It's supposed to help you understand what's going on in the data and show that your measurements are right or not. What you're not supposed to do with statistics is to start with the answer you want, pick a function, and just tweak the knobs until the numbers come out right. Now, we are going into an election year, so all bets are off. But in general, like, machine learning takes kind of the worst practices of statistics and formalizes them and makes them super efficient. So even though, like, we do use some of the same tools here, you know, we use some of the same programming languages, right? The linear regression model actually comes out of statistics. There are other machine learning models that are not really used in statistics. Like a neural network is not something you typically see in statistics work. But there is a considerable amount of overlap. I would just say, in general, in machine learning, you're trying to get the right answers. And you come in with some idea of what the right answers are. Whereas in statistics, you're really trying to get insight into your data. And again, those lines are blurry. There are machine learning algorithms like a decision tree that do give you some insight into your data, but there are other machine learning algorithms like a neural network that really give you no insight whatsoever. They just tend to produce the right answer. And in machine learning, we tend to pick the algorithm that gives us the answers we want. So let's talk about how we evaluate the performance, because a lot of what we do in machine learning is simply to say, are we getting the right answers? And if we're not getting the right answers, what is the nature of the incorrectness that we're seeing? So this red line here is a terrible model, right? It really doesn't seem to reflect the data we're seeing at all. We would call that a biased model because it's really not affected by the data that goes in. Another kind of biased model would be one with a considerable offset like this. So there's a couple other models we could use here. If we take these points here as being our example data, this line with this slight curve in it, that goes through every one of them. I mean, it would appear there that the error is 0. And I said earlier that we don't always want a 0 error. There's another model we can consider here. It's the straight line through there. Now, the straight line is probably a better model. Does anybody have a good sense for why that is? Why is the straight line a better model, even though it doesn't quite go through all the data? Yeah. Well, yeah, it's simpler. So that there's some advantage there, but there's an even more important reason. Sampling errors. So there could be errors in the sample data, and even if the sample data is perfect, we're going to apply the system to other data. And if we hyperfit this model that we create to only the data we train the system with, it just might not reflect data that we haven't seen yet. The goal, what we're really trying to do here is create a system that can predict correct answers for new data. So we don't want to fit the model so tightly to the training data that it's just wildly off the mark for new data. And it's not always obvious when that is. We'll talk about some ways in a little bit to say how do we measure this and how can we see if that's right. So we have a standard workflow we follow when we do these systems. And I'm going to drill into each of these topics separately. So I'm going to just kind of blow by them in this slide to give you the big picture, and then we'll drill down and we'll look at some of the details in a second. We're going to collect the data from whatever source we have. You know, we may have to say how good is this data and how much do we need. We need to prepare the data. We need to throw away things that are obviously wrong measurements. We need to do what we call normalization, which is to take, you know, if you're trying to predict the prices of houses and you have square footage that ranges from, you know, anywhere from 800 to 50,000 feet, and you have prices that range anywhere from $25,000 to $5 million, you probably want to reduce those range, just multiply them so that they fall into a smaller range, like 0 to 1. Some of the algorithms are kind of sensitive to, you don't want price to necessarily be considered differently than square footage or number of bedrooms or bathrooms. So the absolute magnitude of those features is maybe not that important. We do something called reducing dimensionality. I showed you the example of the handwriting recognition where we had 400 pixels for each character. It might be that the pixels in the corner don't actually change the prediction that much. If we can throw away some of those pixels or change their basis so that they affect the system a bit more, we can make the algorithm a bit simpler and a lot faster to run. This all sounds very mundane, but it's actually one of the things we spend the most time on is just cleaning up the data. Then we have to consider our goal. And this is the part that when we talk about choosing algorithms, Azure makes it very easy to compare algorithms, but it doesn't really take the burden off of you to know what the differences between the algorithms are. Azure gives you about 40 different algorithms out of the box. They're split into roughly 4 different categories. This is the place where in Azure, unlike other systems, you maybe don't need to know as much about how to implement the algorithms yourself because they give you pretty good algorithms right out of the box. But you do need to know enough to look and consider what is maybe the correct solution for your problem. Then we're going to train the model, and we'll evaluate the results. Training the model isn't so hard. It kind of comes with the algorithm. But evaluating is actually a pretty complex topic because we don't want to just know is the model correct or incorrect. We need to know when we have an imperfect model, and we nearly always do, we need to say, how is this incorrect? How do we need to change this to make it just a little bit better? And we're just going to repeat that entire process until we're happy with the model that we have. And then we can use the system to make predictions. And depending upon what you're doing, you may want to continuously retrain your model, or you may want to just come up with a model that seems to work and use that same model forever. So you need enough data. What does enough mean? It's not always clear because different algorithms require different amounts of data to work with. Don't go way out of your way in the beginning to find lots and lots of data. You know, if you have 100K of data, that may be enough to kind of say, is this pushing me towards an algorithm that really needs a lot of data for training? Or maybe 100K is just enough. You don't really know until you try. So start with what you can find, and if it becomes clear that you need more data to make your algorithm fly, then you can go get it once it's actually clear that it's worth the effort to do that. So this is a really cool article. It's short, it's a couple pages, it's not super technical. I definitely recommend reading this. This is neat. The way that machine translation used to work is that people would look at, they would build software that would look at a sentence and it would use some knowledge of the language to say, you remember the sentence diagrams you did in high school English class? It would kind of bust it out that way, and then it would map it into the knowledge of grammar, in French or whatever that you're trying to translate to, and it would try and push through something that had a similar diagram, but of course the languages don't have quite the same grammar, so it'd have to do some mapping there. That's not how Google Translate works at all. It's kind of grammar agnostic. What they did is they took the web, and there are things on the web that have been translated, like Wikipedia. And they just said, well, these two articles say more or less the same thing, so go learn that. And it turns out that at a big enough scale, that actually works way better than an algorithm that actually has any knowledge of grammar at all. It's a neat thing, so they call it the unreasonable effectiveness of data. This is not true for every problem. It's not the single solution for every problem we do. It's an example of a case where you need kind of data at that scale to even begin to play in the space. And like I said, in certain cases, a much simpler strategy with much less data is actually going to work better. But for translation, and probably part of the reason this works so well for translation is that translation is not something that we kind of know other good algorithms for. So we're going to talk about data, and this is one of the more jargon-intensive slides. I'm going to try and walk through this. We'll talk about some of the words that I'm going to be using in the rest of the presentation. So this is actually from Azure ML, and this is some data. This is cancer data. In this case, the M stands for malignant. We call the rows in this data set examples. So when you hear example, think of a row or a record. And we call the columns in the data set features. So a feature is just a property of one of the examples. And in particular, this feature on the left side here is special because this is the feature we're trying to predict. And we call that the output or the target variable. And when we're trying to predict the malignant or benign diagnosis, we won't have this column in the data set, right? So because this data set actually has a diagnosis in it, we could consider this a training data set, or sometimes you'll hear people talk about the gold standard. This is something where presumably biopsies have been done, and we know for sure what the correct answer is. We can also talk, there are different kinds of data here. We talk about qualitative versus quantitative data. Quantitative data is something that measures something. So the first column here it's a little hard to read, but this is the radius of the tumor. That's quantitative data. We're measuring the size of the tumor, okay? This column here on the left with the diagnosis, there are only two possible values. You also hear this called nominal or categorical data. Basically, it just means in one pool or the other. It is not a quantity, and you cannot compare greater than or less than. So just a little quiz here. If I'm trying to predict horse race finishes, and I have first place, second place, third place, I'm trying to predict which horse goes in which slot. Is the placing qualitative or quantitative? That's right. Okay. So another thing, another way that we can describe this data here, okay? This is qualitative data. We also say it's two-class data. Not all systems are two-class predictions, but in this case, there are only two classes. There's benign or malignant, okay? Because it's pretty common to want to predict two-class data, your credit card transaction is either probably okay or potentially fraudulent. We have algorithms that are specialized towards predicting two-class data. This is a really common, when we're talking about training data, this is a really common phenomenon called classification imbalance. If I'm trying to predict cancer data, probably there are a lot more benign, hopefully there are a lot more benign tumors in the imagery than malignant tumors, okay? If I'm trying to predict credit fraud, hopefully there are a lot more legitimate transactions than fraudulent transactions, which is all good. It makes me happy for the state of the world. However, if I'm trying to train my system, it's not very effective if I have a massive imbalance in training data, okay? So there are a couple ways that I can deal with this. One way I can deal with this is I can use an algorithm like anomaly detection algorithms that are specialized for this kind of classification imbalance. The other thing I can do is undersample the more common case, just take less of that, and oversample, duplicate some of the records in the less common case to try and bring those a little further into balance. This is all part of the data preparation step in the pipeline. So for supervised learning, so I talked earlier about supervised learning and unsupervised learning, and most of the work we do in machine learning is supervised learning. There's a few cases where we do unsupervised learning, and there's actually a few more that fall somewhere in between those two. But for supervised learning, when I do have a gold standard, when I have those records where some person has gone in and lined them up with the actual biopsy results and given me the correct value of malignant versus benign for the record. You remember I talked a little earlier about overfitting and underfitting? This is how we address that. I'm going to take my data and I'm going to split it. And I'm going to use, the numbers vary, but people typically use about 60% of the data to train their system, okay? When you've trained the system, you want to be able to compare the model that you've built with other possible models. There are many models that you can use. The cross-validation set is a test set for comparing the models, one versus the other, or even tweaking the parameters of the model a bit, okay? And then finally, to see the performance, hopefully a reflection of the performance that you'll see in the real world on the final system, we use another set of data which we call the test set of data. Now in a simple example, people will often only show the training data and the test data, but if you are actually building a non-trivial system, you're going to need to compare one model versus the other, and you're going to need all three sets. Is it clear why we need to do this? We cannot let the data we use for training bias how we do the evaluation of the system. That's really important. If we use the training data in any sense to test the system, it's going to look better than the system's actually going to perform in the real world. Then we can choose an algorithm. This is a portion of the algorithm list for Azure ML, at least as it was about a week ago. This is actually constantly changing. I haven't even expanded the classification node here. There are a couple dozen, I think, algorithms under classification. So we have 4 different, and I'll drill into these a little further going forward, but there's 4 different sort of groups of problems, categories of problems that we can solve with Azure ML. We can do anomaly detection. It's very often the case that you have a lot of data, a lot of examples of things that are not anomalous. And it's very often that the things that are anomalous vary really wildly. So let's talk about credit fraud, okay? If I'm a credit card processor, I have lots and lots of examples of charges that I think are legitimate. Now, if I have a charge that I think is fraudulent, I could put a rule in place to sort of, stop that altogether, because maybe it's clear what kind of fraud I'm dealing with. So in that case, the criminals go home and stop doing crime and get legitimate jobs, right? No, they do something else. So any example I have of a fraudulent charge doesn't necessarily help me to identify charges other charges that are fraudulent, because they just may look totally different. So in that case, I need a type of system that is really only trained with the example of we call that a negative example because there's no fraud, but in the positive examples, I don't really have a good gold standard for that. I really only have a good gold standard for the negative examples. So that's anomaly detection. It's kind of a special case, and there are algorithms that are built for just that system. Classification means we're trying to split into different pools of data. So in the case of the cancer diagnosis, we're trying to split it into malignant versus benign. In clustering, this is an untrained algorithm. We're just throwing a bunch of data at it and say, tell me something about it. I'll show you an example in a bit. And regression is something that I showed you earlier. In regression, we are not trying to predict qualitative data. We're trying to predict quantitative data, and the output of our model is going to be some sort of continuous function like a line. So here's an example of classification. This is a decision tree model, and in this example, we're trying to predict the survivors of the Titanic. And so there are data sets in machine learning that are used for kind of hello world, getting started on stuff. The handwriting recognition is one. The cancer prediction that I'm going to show you in a little bit is another one. And the Titanic survivor data is something that you'll see a lot in sort of intro to machine learning systems. And a decision tree is kind of an interesting algorithm because the decision tree actually does give you some insight into the meaning of your data, whereas an algorithm like a neural network kind of doesn't. But the decision tree, basically what it does is it looks at individual features and it says which are the things that lower the entropy of the data. Essentially, which are the things that make the biggest difference in how it does a cut between one pool of data and the other. And it tries those iteratively, and then it builds a tree up. So in this case, it says that if you are female, you probably have a better chance of surviving the Titanic disaster than if you're a male. You know, women and children first, right? Your age affects that, and whether or not you have a sibling or a spouse on the ship affects that as well. So that actually gives us a little bit of insight into the data. This is not a perfect system here. If I look at these numbers, this number here on the left is on each node is the probability of survival, and this is the percentage of observations in the data set. So it doesn't totally, it's not a perfect model. It doesn't tell us everything we need to know, but it's interesting because it gives us a little bit of insight in a way that other algorithms might not. So here's an example of unsupervised learning. This is k-means classification. Basically, we just throw a bunch of data at the system. We have no gold standard. We have no example of the thing we're trying to predict, which in this case, we're just saying separate this into different groups. And you can imagine situations where it might make sense to do this. If you're trying to break down pricing into different pools of prices, or if you're trying to break houses into different markets, things like that. Did you have a question there? Yeah, I can. So the probability is based on, so in this case, we actually know the outcome for every person in the data set. So the probability is just based on real world there. In this case, we're not so much predicting the survivors of the Titanic because it's 100 years ago, but we're trying to get some insight into the data. So yeah, in other kinds of predictions where we're trying to predict data we haven't seen yet, then we don't know that. So it's kind of it's an interesting observation there because this is really a special case. So this is, as I said, this is unsupervised learning. A couple cases of hybrid algorithms that are sort of partly supervised, partly unsupervised. I already gave the example of anomaly detection. Another thing you see a lot is recommender systems. So things like on Netflix, you see, here are the movies you might be interested in. The interesting thing about that problem is that it's influenced by the movies you've rated, but Netflix has lots of movies. It's got hundreds of thousands of movies. You've rated maybe 100, 200. So there's some data there that's useful, but not really enough to make a prediction that's definitely going to be spot on. The other thing is that it doesn't have any insight into the films themselves. You can categorize them maybe into romance or thriller. There may be some overlap between there. That's not really enough combined with just your ratings to say what you're going to like. So we do something called collaborative filtering or collaborative recommendation that essentially can extract features from the films and figure out what features you like in a film at the same time. It's kind of interesting because we're trying to predict two things at once. So that's kind of a blend between supervised and unsupervised. We have some data that says what kinds of films you might like, but just not very much. So here's an example of anomaly detection. This is an exercise that you complete in the Coursera machine learning class. And in this case, we have lots of examples of things we call these negative examples. These are things that they all kind of resemble each other a little. And then we have these things on the outside that for some reason they just look different. Okay? So if you are a credit card processor, you probably want to give these customers a phone call. If these are insurance applications, you probably want to send these particular policies to the underwriter before you just write the policy. These are things that they look different. We don't know why. They probably need deep examination from a domain expert. Yep. So the rings are probability densities. So these are things, it kind of says how self-similar they are. So basically, to what degree is this record different from the other records in the data set, where different is the cost function you write. And basically the further out, the weirder the record looks, to the point where, maybe this isn't fraud, maybe this is just bad data. So cost is a function of the prediction versus the output versus the gold standard, and it's kind of arbitrary. There's not one correct cost function. You pick the one that gives you the best model, but in general, you do something like this. You say, for a particular point in the real-world data, if my model is the straight line here, the cost might be the difference between that point where it really is and the prediction that the model makes at the same point on the x-axis there, so this little interval there, squared. Okay? I do that for each point in the training data set. Then I sum the whole thing up. And so the sum of the squares of the difference between the model prediction and the real world, and I'll often do something like, you can divide by the number of examples so that the cost doesn't change with the number of examples you have. You can throw in coefficients. It doesn't matter. I can divide the whole thing by 2 if that makes the calculus easier. Again, you don't actually have to solve this with Azure. It's built in. But if you're implementing the algorithm yourself, you can pick whatever cost function kind of works. The important point is that the better the model is, it should tend close to 0. So most, if this is my model here, this is a terrible model. The cost of that is essentially infinite. The cost of this model and the training data that zigzags is 0, and we said earlier that that's probably not a good model, and the way I detect that is by using cross-validation data. And then there's some positive cost to the straight line model, but it's not super high. And if I test that against the cross-validation data, again, it probably has a lowish cost. And most machine learning training can be just expressed as minimizing a cost function by tweaking the parameters of the model. So now we need to evaluate the model. And that sounds like it ought to be kind of easy. It sounds like, it's lowest cost. It sounds like, am I getting the right answers? But it turns out that's actually kind of complicated because it varies a lot based on what kind of model you have. The cost function of a linear regression model, like the one on the previous slide, maybe I can just look at that in terms of sum of squares of differences. And a classification model, I might need to do something a little bit different. So this is something called a confusion matrix. This is a common way of evaluating classification models, and this is Azure ML that we're looking at here. And basically, this is the gold standard class on the left here, and this is the predicted class by the model on the right. And when you see values on the diagonal, that is awesome. That means the model predicted things correctly. If you see values on the that are not on the diagonal, that means we have an incorrect prediction. And it's worthwhile to look at this when you're doing classification training because it can give you kind of insights into the data, into the errors you're seeing in the data. So one thing that you might see is if you're doing handwriting recognition, a lowercase c looks a lot like an uppercase C, and you might not be so concerned about that error because you can fix the casing in a just imperative code. But if you're seeing, well, the character S is being confused for the letter I, that's maybe an error that you're a little bit more concerned with. So looking at the confusion matrix is useful, but ideally in this case we want everything on the diagonal. This is also Azure ML, and this is something called the receiver operating characteristic, or ROC, which is a weird bit of terminology. It comes out of radio research that was done kind of in the 1940s. And I bring up the term only because when you do actually hear about ROC and AUC, and they show AUC is the area under the curve here. These are terms that do show up in Azure ML. They're kind of strange in that receivers are not something we're normally dealing with in the models we build. But this is actually a really important graph here. So if I look at the axis on the left, that's the true positive rate. So in this case, we're doing two class. You see this curve when you're doing classification with a two-class algorithm. So you're benign versus malignant, fraudulent versus non-fraudulent, cases where there's essentially four possibilities coming out of your model. You can have a true positive where the model predicted positive and the gold standard was positive. True negative where the model predicted negative and the gold standard was negative. A false positive where the model predicted false positive, where the model predicted positive and the gold standard was negative. And a false negative where the model predicted negative, gold standard was positive. So four possible characteristics. The axis here on the left is the true positive rate. It's how well your model did at how well did your model predict positive for examples that are supposed to be positive. And the axis along the top is the false positive rate. The point of all of this is that depending upon the situation you're in, if the model's going to make an error, it might be better for you to have a false positive than a false negative or vice versa. If I'm looking at imagery of possibly malignant tumors and the people who the model predicts positive for are going to get a biopsy and the people who the model predicts negative for are not, would I rather have a false positive or a false, ideally, of course, I want to get it right, but would I rather have a false positive or a false negative if there's going to be an error?
False positive.
Yeah, I mean, you can actually make an argument either way. I would say you probably want a false positive because you probably would rather get the biopsy and be told you have no cancer than just miss it. But you could also make the case that biopsies are pretty invasive. The models aren't. This is probably something that me as a programmer, I should not be the one to answer this question. It's probably best left to a domain expert. But I would suspect we'd prefer to have a false positive in this case. So the area under the curve is kind of the amount you got right. And it's hard to see on the slide with the projector, but there's a line here that's really light that just goes diagonally. This is essentially the kind of model you would get through pure random chance, through a coin flip. So you want to be doing better than that. The bigger the area under the curve, the better your model is. But again, the particular slope of the curve kind of tells you, does your model tend to predict false positive or tend to predict false negative? So we talk about recall and precision as ways that we can characterize the model. And this actually gets into the things that are a little hard to follow, but it's very important. So I have three classifiers here, and these two are not great classifiers. One classifier responds positive to every example it sees. It's simple to write, but probably useless. One classifier responds negative to everything it sees. And then I have a machine learning model I built. These are actual results from Azure ML that tries to pick the best answer. And the reason I have these two kind of stupid-looking degenerate classifiers is that they do kind of tell you how the metrics that you see in the evaluation on Azure ML reflect data that you might actually see in the real world. So if I have one of the metrics we use is accuracy, and that's simply the ratio of records where we predicted the correct solution. And that seems like it ought to be a really useful metric, but it kind of turns out to be less useful than you might think. One reason is that if you think about classification imbalance, so my credit card fraud examples, even if I oversample or undersample my data, I still probably have a lot more non-fraudulent transactions than fraudulent transactions. And if my model simply has a big bias towards returning not fraudulent, the accuracy is going to look really good, even though it's not really a very useful model. It simply is reflecting the data I'm training it on instead of the usefulness of the model. So accuracy is neat, and it's something you can use to sell the system to your executives, but it's not necessarily going to help you predict choose the best model for the problem you're trying to solve. It might be the most important thing in the very end, but it's not so useful in evaluating the individual models. So, you know, in this particular example, if I have a system that always returns positive, accuracy of 0.4, that's just, it's not reflecting my data very well. Recall is the ability to find positive examples, and of course a system that always returns positive has a perfect recall, okay? Precision is the ability to get stuff right in a system that, well, it avoids false negatives, and, you know, again, always negative, not so great. The machine learning model actually, though, has pretty good accuracy and precision, and there's something called the F1 score that tries to roll those two things together. And again, the machine learning model looks pretty good on those. And the end result of the system here is that we end up with a system that maybe makes the best use of the resources we have. So that's the theory. Let's put this into practice. So this is sort of interesting for everyone in the cloud track. This theater it's got great projectors, it's got good sound. What it does not have is internet at all. I could possibly tether, but I have T-Mobile and I'm outside of 270, so all bets are off. So this will be kind of a whirlwind tour, and we're not going to cover every possible feature. What I did is I made some screencasts, because those will actually roll, and I can kind of explain what's going on, and I don't have to worry about my internet service being interrupted. When you think of Azure, you don't tend to think of an inbuilt web-based IDE, but that's exactly what you get from Azure ML. The algorithms come out of real-world use in things like Xbox and Bing. There's first-class support for both R and Python. If you want to do things that are not built into the system, you can add scripts in languages that data scientists tend to know. And you can take data from many useful places, including the web, or if you have stuff in SQL Azure or Hive, you can use it there. And let's just roll through a demo real quick. You need to have an existing Azure storage account. There's a feature built in that'll create it for you, but creating an Azure storage account takes about 20 minutes or so, and the machine learning tools don't handle that time delay very well. So I would just create it first if I were you. We're going to create an Azure ML workspace, and we're going to launch the ML Studio. So this is the Azure Manager. You've probably all seen that. I'm going to go and create a new ML workspace. I'm going to type in a name. We're going to call this one Stir Trek. We're going to launch ML Studio, which is kind of a totally separate environment. All right, so now we need to create a new experiment. You can create many experiments in a workspace. You're probably going to want to play with different models. And also, in the real world, ML systems tend to have a pipeline where you might want to look at so in this case here, I'm adding data to the system. For the cancer prediction, I'm going to use one of the out-of-the-box data sets they give you with ML Studio. In the real world, you probably want to upload your data. And then I'm going to split that data. We talked earlier about splitting it into test and cross-validation and training data sets. So I use two of the split modules, and I'm going to split it 60-20-20, training, cross-validation, and test. So what I was saying earlier is that, you know, if I'm trying to read signs on Street View, I might have one part of the pipeline that finds the sign, and another part of the pipeline that breaks it into characters, and another part of the sign that tries to read individual characters and turns them into letters. And so I might have multiple experiments in the workspace for that. So what's in this thing? I can go ahead and visualize some of this data here. I'm going to click there, and I'm going to click Visualize. And this is the screen I showed you earlier on the slide. By clicking the column, I can get a histogram to see what kind of data is in there. And it only shows me about 50 records in this view, the histograms for the entire data set. But if I do want to do some more detailed analysis, I can download the data. I can open it up in R or Excel. So now we can do machine learning. I'm going to zoom out for a little bit more room. I need to choose an algorithm. We need a two-class algorithm for predicting malignant versus benign tumors. I'm going to start with the decision tree algorithm. I can just drop that into the workspace like this, but it is not trained at this point. So I'm going to add a module to train the algorithm. There's a train model module. And to that, I'm going to connect the untrained algorithm, and I'm going to connect the training data set. That's about 60% of the data that I have. And then I need to tell it which column, which feature I'm trying to predict. So I open that column selector, and I predict class. Next module I'm going to add here is the score. This is the thing that compares the predictions from the model with the cross-validation set there. So I connect both data sources into the score module. And then finally, to see how well I did, I need the evaluate module. So I'll drag that on there. And that's all I need for now. I don't need to connect the other connector. Let's take a look there. I'm going to run the experiment. Just click run. This can take a while. It depends upon the algorithm you choose, and it depends upon how complicated your system is and how much data you have. This one's going to run pretty quickly. There are only a couple thousand rows in the training set, but I have used much bigger training sets with more complicated algorithms, and it can take many minutes in hours, possibly, depending upon what you're doing. But these little, there were little clocks on the side here that have all turned into check marks, so I'm done running. Let's see what we have. I'm going to go to the evaluate module, and I'm going to click visualize. And there you see the ROC curve that I showed you earlier. This one did pretty well, right? There's a little confusion matrix down here, which shows me my true positives and my true negatives. And the false positives and the false negatives don't look so bad. I can also see the area under the curve of 0.995, which is excellent. So without having to do a whole lot of tweaking, I came up with a system here that does pretty well. And part of that is that I just happen to know a module that would work well, because I've played with this thing a lot. I've played with this data set and with Azure ML a lot. In the real world, I'd probably have to do experiments with other modules. So if we're satisfied with the experiment, we can convert it into a couple web services. I might want a web service for retraining the model based on new data, and I might want another web service for actually making predictions. In this case, I'm just going to click Prepare Web Service. This is my training web service. If I come up with new diagnoses from actual biopsies, then I can retrain the model to make it hopefully more accurate. And I could change the name of the published web service arguments, but for now I'm just going to take the defaults and I'm going to publish it. Okay, so there I have some endpoints that I can use for training the model. We have about 3 minutes left, so I'm going to race through the rest of it. Now I want to make a scoring experiment for predictions. This is actually going to be a brand new experiment. It is not going to have the training data in it. It's only going to have a web service endpoint. So if I click, I'm going to click Create Scoring Experiment there. You see now I have some tabs on the top for the training experiment and the scoring experiment. I can flip back and forth between them. Run the experiment. Now I have something that I can use in Excel or any language to actually create, to actually make predictions. And it will give you sample code out of the box, which I can show you on the laptop later when we have more time, if you'd like to see that. There's a gallery that allows me to share the experiments as demos for other people. This is a good place to look in if you want to see how to do a particular kind of work in Azure. And some of the features I'm not going to have time to talk about too much today. I can write arbitrary scripts in R or Python and have them run within Azure ML. If I need to do something that's not available out of the box, I can create entirely new machine learning algorithms that way. I can integrate with SQL Azure. Sweep parameters is pretty cool. I can connect that to my model, and I can just experiment and see which give me the best result. And if I want to throttle different customers, I can go back to the Azure Manager, and I can create different endpoints for each customer, and I can throttle them individually. Another feature that Azure ML has is lots of bugs. It's not quite, it's supposed to be out of preview, but I hit bugs almost daily, and some of them are really amusing, like the one on the screen here. Bottom line, there's a free tier that you can use for experimentation. It works pretty well. It just restricts the size of what you can do and how much you can hit the thing. These are the prices as of about a week ago. They're changing all the time, and they're changing kind of everything, actually everything in Azure ML. We get new algorithms. Other algorithms go out to pasture. The prices change. It's very much in flux now. I don't even know that I'd necessarily recommend it for a production system just yet, but it's getting there. It's getting better every day. I can compare this a little bit. Amazon this past week announced a competing system, but theirs is a lot more limited. It's kind of like Azure ML as of a year ago. It really only does regression right now, and it doesn't have the customization in terms of running custom scripts that Azure has. But if you are already in the Amazon ecosystem and you need to do regression, it does actually work pretty well for that, it seems like. I could also do machine learning on my local machine using MATLAB or Python. I typically have to do some more work to make that go, and I don't have the Azure infrastructure, but it's a nice option if I need to keep all my data in-house. And I'm getting really at the end of my time here, but I'm just going to blow by this. If you're looking for references to learn more, download my slide deck and go through some of these resources here. This is how I got started. If you want to reach out to me and you have questions of things that I didn't get to during the presentation, I'm going to be here all day. I'd be more than happy to sit down with you. I don't know that I'll necessarily be able to get a good web connection to demo this live. But I can meet you at your place of work or whatever if you'd like to go through and see more details here. You can reach out to me on Twitter or via email. I'm also the co-founder of a group in town called Papers We Love for people who like to read academic computer science. And if that sounds interesting to you, I would love to have a conversation. So thanks a lot for coming out for the math lecture first thing in the morning. I really appreciate it. Enjoy the rest of Stir Trek. Thank you.